Good afternoon, bon après-midi. Welcome to this edition of the Physical Society Colloquium. I'm coming to you live from the brutalist majesty of the Rutherford Physics Building at McGill University in beautiful downtown Montreal, where clever people have been learning and researching for what seems like longer than a neutron lifetime. If you are in the Zoom session and prefer not to be recorded or live streamed, please log out of Zoom and join us via YouTube. This afternoon, we will have a 45-minute talk followed by 15 minutes of questions and answers. To ask a question in Zoom, please use the raise hand feature following the talk. To ask a question in YouTube, please enter it into the chat. The questions will be relayed to me by my sidekick following the talk. After the Q&A session, the live stream and recording will stop. Professors will be asked to log out of the Zoom session, and undergrads, grads, and postdocs, as well as other non-faculty in the Zoom session will be invited to the après colloque, a chance to get to know the speaker in a more intimate setting. With that, I will now pass to Professor Thomas Brunner to introduce the speaker. Thomas.
Thanks, Bill. It's a great pleasure to introduce Nadia Fomin from the University of Tennessee. Nadia is a professor at the Department of Physics and Astronomy, as mentioned, at the University of Tennessee in Knoxville. And her research is on life and death of neutrons that she will talk about today. A little bit about her biography. Nadia did her bachelor's in physics and computer science at Georgetown University, and she received her degree in 2000. As an interesting side note, is that she actually started out as a government major. She did a bunch of political internships before she actually saw the light and really focused on physics. After graduating with her bachelor's degree, she worked for Lockheed Space Operations for 18 months, and then in 2001 started graduate school at the University of Virginia in experimental physics. Her thesis work actually focused on short-range nuclear-nucleon interactions, and this work was actually done at the Jefferson Lab. Following her graduation in 2008, she did a postdoc with the University of Tennessee and Los Alamos National Labs, and that's actually when she got into fundamental neutron physics, the field that she is still researching in. In 2013, she became a faculty at the University of Tennessee. And yeah, I'm very excited that she will be joining us today and talking about her research. So welcome very much. Welcome very much, Nadia, to McGill. And we're very excited to hearing your talk.
Okay, thank you for the introduction. And I do hope that you guys have been researching physics for longer than the lifetime of a free neutron, because that's only about 15 minutes. So, so I have a fancy title for my colloquium today, but basically it's code for we're going to talk about neutron beta decay. And just a little background about myself, as Thomas mentioned in the introduction, I kind of have two areas of research in experimental nuclear physics. One of them is fundamental neutron physics, which I'm going to talk about today, but I also study short-range nuclear and nucleon behavior and nuclear medium effects at Jefferson Lab in Virginia. Specifically, nuclear medium effects, I mean, like, hey, this quark is bound in a nucleon, but if this nucleon is also bound in a nucleus, those quarks notice that, and we can observe the difference in the data. So just a little bit about me. And I hope very much that the talk I've created today is a colloquium. So it's not for experts, and I will hopefully follow the ideal understanding graph. This is the slide where we're going to start with 100%. And towards the end, we'll, get back up so that, we all feel like we learned something. I stole this from this article about 9 kinds of physics seminar. I think it will resonate with everyone. If you Google for it. Okay, so let's talk a little bit about the history of neutrons. It's been over 100 years since Rutherford first observed that the atomic mass and the atomic number are not at all the same. And just doing some simple math, one can tell that electromagnetism alone is not enough to bind a group of positively charged particles and negatively charged particles into a nucleus. So he first suggested the existence of a heavy neutral particle, but the big difference from what we actually know today is that his suggestion was this particle would be a bound combination of an electron and proton. If that were true, that would mean that the mass of this heavy neutral particle would be less than the sum of the proton an electron, basically less than the proton, because the electron mass is very small by comparison. If that were true, if this were a bound state, then it would be impossible for this neutron to decay into a proton and electron by itself. And from the title of my talk, you know that this is not the case. And this idea of a neutron as an elementary particle was not met with universal acclaim at the time. Chadwick himself was very skeptical. He said, of course, it's possible, but there is no reason to actually think that it's true. And he is the one whose work then discovered the neutron. Not quite 100 years ago, but getting there. And a few years later, the masses were measured precisely enough that we now know the mass of the neutron is greater than the mass of the proton. So it's not a bound state of a proton and electron. So this is the first suggestion of neutron decay, that free neutrons would decay. And the first experiment, as you can see, is well over a decade later. Because to measure the neutron lifetime, to observe neutron beta decay, you need a source of neutrons. This first, so I am at the University of Tennessee. Well, I'm actually at my house, but the University of Tennessee is about 25 minutes or so from Oak Ridge National Lab, which was originally built and had the name of Clinton National Laboratories. And this is where plutonium was, with the plutonium enrichment effort was going on during the war. And after the war, this reactor was repurposed for research. And one of the first things that was measured here was the neutron lifetime. If you can see, you're looking for a number and you're looking for errors. And the best we see here is that it's greater than 15 minutes. Between 15 minutes and 30 minutes. So pretty big error bars over here. And this was published in 1948. Ooh. So today we can use that neutrons are very versatile in nuclear physics. We can use them to make measurements of all the 4 fundamental forces. I'm going to talk about the weak force, specifically neutron beta decay. But I did want to mention a little bit, just because it's so cool, how neutrons enter into, how neutrons can be used to probe gravity, because it's kind of a recent development. So these experiments, it's called gravity resonance spectroscopy. So the idea is to use ultra cold neutrons. We use temperature terms, but an ultra cold neutron is just a very, very low energy one. When I say low energy, I mean nano electron volts. So it wouldn't be able to bounce more off of a table than, tens of centimeters. So the idea is to use them to probe energy eigenstates in the gravity potential of the Earth using this technique. So these ultra cold neutrons, these very low energy neutrons, can actually bounce, undergo total external reflection off of specially prepared materials that we called mirrors, because they reflect neutrons. What we can do is then in this experiment, they actually shake the mirror at the frequency that corresponds to energy transitions between the quantum states of the neutrons in this potential. So you prepare some state of neutrons, and then it transitions into another state, and then we only transmit the original state back to the detector. So basically what we're looking at to see is if this mechanical oscillation is exciting the neutrons to the next energy levels by observing the transmission of the original state. And so this is kind of a tabletop experiment, actually. And this is what the transmission as a function of frequency looks like. You can see the transmission is flat, nothing is changing. And when you hit the right frequency that corresponds to that energy level transition, there's a dip in the transmissions, because now those neutrons gain energy and they are no longer transmitted forward. So the cool part of this is, of course, not that, neutrons have energy levels, but that you can affect them with a mechanical oscillation. So, and there's potential interesting for future prospects for these kinds of measurements. But getting back to what we've been doing here in Tennessee, and in the first two neutron experiments were measuring the neutron lifetime, and the other one was measuring the electric dipole moment of the free neutron. So both of these are published in the local news, and a lot of fundamental neutron physics research today still focuses on measuring those two quantities. So if this sounds interesting to you, there's great job security in the field. So before I get into the details, I mentioned this somewhat, but I just want to give folks some terminology so that it all makes sense going forward. So the neutrons that we're talking about are primarily going to be cold or ultra cold. And this is just has to do with their energy range. So they're milli-electron volts or even lower, and ultra cold, like I said earlier, is in the range of nano-electron volts. So these ones, the ultra cold neutrons are moving at single digits meters per second, whereas the cold neutrons are moving at about 1,000 meters per second or so. So very easy to imagine velocities. Okay, so why do we care about free neutron beta decay at all? Why are we still measuring the neutron lifetime after more than half a century? Well, neutron beta decay is really the simplest form of beta decay. So in that sense, it's a prototype for all weak decays of hadrons. It is an input to the standard model of particle physics, which we'll talk a little bit more about. And it is also an input to the Big Bang nucleosynthesis models. The lifetime of the free neutron is important to understanding the early universe. So the thing that actually happens in neutron beta decay is one of the down quarks into a neutron becomes an up quark, making it a proton via the emission of a W minus boson, which then decays into electron and an antineutrino. So this kind of sets the stage for our experiments. So I'm going to talk a little bit more about some of these motivations, and I guess I'm going backwards because I'm going to start with Big Bang nucleosynthesis. So where the neutrons are useful are kind of in this region where you can see nucleons are starting to form, and then nuclei are also starting to form. So you see the green and the pink ones here are neutrons and protons. In about 3 minutes, you can see that they're starting to bind up into light nuclei. So how does the neutron lifetime come in here? Well, once nucleosynthesis begins at about 10 to the 10 Kelvin, we briefly have something called a weak freeze out, where the ratio of the neutrons to protons, which is at this point set by their tiny difference in their masses, stays approximately constant for just a little bit, just because it's hot enough that while neutrons can decay, you can go back to neutrons via electron capture. So nucleons are free and their numbers are small. But this is a very brief moment in time. The universe is expanding, the temperature is dropping. So as you can see in this plot, which the numbers are actually getting smaller as you're going to the right, but it's also because it's temperature, but it's also time, right? So as the temperature is dropping, we're moving forward in time. And the neutron abundance, it's this red line here, you can see it's going down because neutrons are both decaying, because free neutrons will decay, but they're also being captured in light nuclei. And at about 5 minutes or so, almost all neutrons are bound up in helium-4, and just a few minutes after the Big Bang, you basically have final freeze out. So the ratio of the helium to hydrogen in the early universe is set by then. So you can imagine how knowing the lifetime of the free neutron is important in these calculations and in understanding what is going on in the early universe. And right now, oops, too far. And right now, the uncertainty in the lifetime of the free neutron is the dominant one in these calculations. After 60 years, a little bit embarrassing, but I'll show you why that's still the case later. The other part of the motivation comes from trying to understand particle physics in general. So our particle physics understanding is formulated inside the standard model of particle physics, including for neutron beta decay. We have this matrix that describes the mixing between the quarks. And there are these, there are the elements of this matrix. They have names with subscripts that correspond to the mixing. Their subscripts tell you which two quarks we're talking about the mixing about. As you can imagine, from the subscripts and from this picture, neutron beta decay measurements can give you a lot of insight into this element called VUD. In the standard model, this is a unit. This quark mixing matrix is unitary, which means that the sum of the squares of the elements in a row should be 1. So by doing neutron beta decay measurements, we can check that it is, or even more interestingly, maybe we can find out that it's not. It's pretty straightforward. A lot of constants have already been plugged in here, but basically the VUD element of this matrix is, as I said, these constants, the neutron lifetime, and another parameter that has to come from a different measurement that we call lambda. But it also comes from a beta decay measurement. So if we do these two measurements, we can determine this element in the quark mixing matrix. And it's a big one. It's like literally, they add up to 1. This is greater than 0.9. So it's the dominant one. So what can we measure other than the lifetime of the free neutron? So looking at this picture, we have electrons. We can measure the momentum of the electrons. We have neutrinos, we have protons, and we have neutrons. And in the neutron measurements, our beam of neutrons can be polarized. So there can be a spin degree of freedom in our measurements as well. This is I'm not going to show a lot of equations because I'm an experimentalist, but this is one I have to show. So this is the expression for neutron decay rate that was originally published in 1957 by Jackson and Associates, the same Jackson who wrote the electromagnetism textbook. Okay, so sorry, I see a thing in the chat. Let me see. Doesn't it have to be squared? This one is squared. I think this is, this guy is squared. So, so going back to this expression, it's proportional to some density of electron energies. And then there is, these are just the leading terms in our decay rate equation. And staring at it, I can draw your attention to the important pieces. These are called correlation parameters. And these are the things that, in addition to the neutron lifetime, we can measure experimentally. And by staring at this equation some more, we can kind of tell what they are. So you can see, for example, little a is the correlation parameter between the electron and neutrino momenta. So in this picture, you can see it's kind of related to the opening angle of the two. Then there are quite a few correlation parameters that have to do with the spin of the decaying neutron, and then the electron momentum or antineutrino momentum. As you could probably guess, we don't even try to measure the neutrinos. We focus on the electrons and the protons. So to measure VUD itself, we need lifetime and lambda, and I'm going to tell you what lambda is now. It's the ratio of axial to vector couplings in the weak interaction. And by measuring, for example, one of these correlation parameters, it can be rewritten as a function of lambda. And so can A, and so can B, for example. But I'm not going to talk about all experiments. I'm going to focus on a couple of beta decay experiments and how they're contributing to the field. So, so lambda is this ratio of axial to vector couplings. I didn't write down another equation, but the neutron lifetime is actually a linear combination of the same two couplings. So if you measure the neutron lifetime and lambda via one of these correlation parameters, you basically know everything that you can know about neutron beta decay. So that's what we want to do. We want to do both kinds of measurements. So I teach the class I teach right now is senior physics majors. So I wanted to scar them a little bit. So I showed them the standard model Lagrangian. I think this may have all the terms. I think it does. But basically, when I go and tell people, yes, we are measuring parameters in the standard model. So there's 26 of these whose values have to be gotten from the experiment. And we call them we call it VUD, but they can also be rewritten as the actual angles, the actual mixing angles in the quark mixing matrix. So actual parameters into the standard model. Okay, and what is the landscape? What does the experimental landscape actually look like? Well, the best way to do this, to get VUD, is not actually with the neutrons, neutron beta decay. It's actually with 0+ to 0+ decays, nuclear beta decays. The experimental uncertainties are much lower, and we still have a ways to go to catch up to them. The thing that makes neutron beta decay an attractive lab for this is, as you can see, we don't have this nuclear structure uncertainty because there isn't any nuclear structure. So it completely removes this interpretation sort of correction from a neutron beta decay measurement. So the next, the set of the two experiments that I'm going to focus on, which are kind of happening now or will be happening in the next couple of years, are going to take us to this target uncertainty. This in particular has to do with the neutron lifetime. It's quoting at 0.2 second uncertainty with the neutron lifetime because it's kind of easy to understand. But the other beta decay measurements will have matching uncertainties. So this is a very exciting time going forward for neutron beta decay experiments. It's recently has gotten even more exciting. So this is a plot I showed, I think, a couple of years ago showing VUD as a function of lambda. And lambda is the parameter we get from decay correlation experiments. So this is the value, the blue line is the value of VUD as extracted from nuclear beta decay measurements. And it's well defined, it's narrow, the uncertainties are low, and this gray line that intersects it is what is required for CKM unitarity. So everything looks good. The standard model is fine. VUD parameter is well known and consistent with the standard model. And these are results from various neutron experiments. This is the neutron lifetime for the particle data group. And these are some of the more recent results of lambda. And they're like, yes, you can do a giant circle where these all intersect, and it's fairly consistent with the standard model as well. So this is my updated plot now. There have been some theoretical developments to the radiative corrections for beta decays that have actually moved the results, the experimental results, out of agreement, out of what's required for CKM unitarity. There is a new neutron beta decay measurement that has measured little a for the first time. These other ones were measuring a different decay correlation, and they were basically consistent with each other. And this is the first measurement that measures this electron and antineutrino correlation, this opening angle between the two particles. So now it's looking a little messy. So as experimentalists, we want to do more measurements, of course. Neutron decay measurements that are happening or recently did happen, and I did focus in the US because these are the ones that I am primarily involved with. So in Eastern Tennessee, we have the spallation neutron source at Oak Ridge National Lab, and this is where the NAB experiment is getting ready to commission. The upside is that now that I showed you that one equation, these are not creatively named. You can tell exactly what we're measuring. So we're measuring the little a and little b decay correlation parameters in neutron beta decay. The Acorn experiment has recently published their result. They're also measuring the little a correlation parameter neutron beta decay, but they were not competitive with their uncertainty. So I don't include them in that plot because it's most of the plot. And then at Los Alamos, which also which uses ultra cold neutrons, we use cold neutrons for these two. They had a program to measure both A and B in ultra cold neutron beta decay, and there's talk about an upgrade path for those measurements. So this is where the neutron facilities are, and this is where the experiments are. And I, being in Knoxville, I do quite a bit of my work at the Despelation Neutron Source at Oak Ridge National Lab. It's an accelerator-based source, operates at 104 megawatts. And as is the case with most neutron sources, we're nuclear physicists, but these are not nuclear physics facilities. These are primarily condensed matter materials facilities, or even these beamlines exist even for biology research. They have permanent installations. They do certain kinds of measurements. And we are lucky number 13. We are the fundamental physics beamline. I guess it's more than 10 years later, the staff is finally getting used to the fact that we build a new experiment every few years and change everything out. But it's a very different place to work than a nuclear physics laboratory. Okay, so this is going to be the home of the NAB experiment, where we want to measure that little a correlation parameter, which is the opening angle between the electron and the neutrino. Since we don't detect the neutrino, to know anything about the neutrino, we basically have to detect everything else, the proton, the electron, and know something about the neutron. And with energy and momentum conservation, we can solve for everything we need to know about the neutrino. So what we do is we have this neutron beam that comes in. And for me, when I switched from doing JLab physics to neutron physics, this was kind of very anti-intuitive. The neutron beam is this big. It's 10 by 12 centimeters. It's huge. It's not, you know, a few femtometers across. It's huge. So the neutron beam mostly passes through our experimental apparatus. What we're looking for is any protons or electrons that appear from neutrons that decay while passing through the apparatus. We have built an electromagnetic spectrometer to capture them and detect them. And I just want to talk a little bit about the cute part of this experiment. So detecting electrons is pretty straightforward. Detecting protons from neutron beta decay is not. The endpoint energy of protons for neutron beta decay is 750 electron volts. If you're not calibrated for that sort of thing, it's a very, very low number. With the same detector that I'm detecting my electrons with, that has kilo electron volts, the proton won't even get through the dead layer, much less create a signal. So one common aspect of all these neutron experiments is that the detector sits at high potential, at least 30 kilovolts. And that means that at when the proton gets to the detector, it sees this kick of 30 kilovolts, and then it loses about a third of it traversing the dead layer of the detector. So in the end, we still are detecting very small signals. The cute part of this experiment, though, as I said, is that we're trying to detect the momentum, not the energy of the protons. And if a neutron decays in that volume, the proton momentum can be going into every which way direction. So the magnetic field is designed in such a way that there's a pinch kind of in the middle. It knocks out about half of our protons. It rejects them based on, it's kind of like a momentum selector. And then the remaining ones are slowly processing around the field lines as they're getting to the detector at the top. We can't change their energy, but we can change the direction. We can't change their velocity, but we can change the direction of their velocity. So what we're doing is we're slowly longitudinalizing them. So by the time they get to the detector, they're perpendicular to the face of the detector. So we're not detecting a component of their momentum, but their whole momentum. So that's kind of the big cute thing about this experiment. And for experimentalists in the audience, the other neat technological thing for this is that our detectors are big. They're 11 centimeters across, and they're single crystal silicon. And to because our proton signals are so small, we have to keep this low noise. So they actually have to be pixelated into 127 pixels. And this is fairly new technology that was pioneered by the UCNA and B collaboration, but also by the Katrin collaboration. And that's what we'll be using for NAP as well. It actually mostly exists in real life. I couldn't tell if you could see from this picture that, this is asymmetric. How big is this thing? This thing is really big. So this is the floor of our experimental area. This is the beam port. It's 6 feet off the ground. So the whole magnet, I think, is 7 meters tall. And a collaborator who's from Louisiana snuck in Mardi Gras colors for the design. So we didn't notice until it was too late. But this is what it looks like in real life. I also wanted to just show you pictures of these detectors. This is the back of the detector showing the pixelated readouts. The front of the detector, I didn't know this. Single crystal silicon is actually very, very shiny. This is a reflection of the ceiling. That's not what the thing looks like. And there's just a lot of consideration. The detector has to be cold, so it lives in this like copper sandwich that we then try to cool by flowing helium, which is a system that my graduate students had to build. There's them working really, really hard. I always want to give them credit and show what they've designed and done. And also, just in case I'm not keeping to my ideal understanding versus time scenario, in case I am the unprepared experimentalist from that same article, sneaking in the picture of our lab facilities in Tennessee can cause 100% understanding spike. So this is my backup. Okay, so that's the NAB experiment. That's one way to measure one kind of correlation parameter in neutron beta decay. And that's honestly kind of a new way to do it. For the last few decades, folks have focused on measuring big A, which is the correlation between the neutron spin and the outgoing electron momentum. And so most of the values of lambda that exist so far have come from those measurements. Okay, oops. So we talked about how to do lambda. Let's talk about how to measure the neutron lifetime. There are two ways. And it's the same way as you would measure the lifetime of anything radioactive. You can get some quantity of the radioactive thing, see how much there is, wait a few half-lives, by which point the quantity should be greatly depleted, and check again. That approach works if the half-life is not too long. Like, this is not a good way to measure the half-life of plutonium, which is like 10,000 years old. You can't just wait a few half-lives. But luckily for the neutron, it's, and I will mostly say the word lifetime, which is not the same thing as half-life. There's like a square root of 2 in there. So the lifetime of the free neutron is about 15 minutes. So this actually would work fine if we could get like, a jar of neutrons, wait a while, wait a few 15-minute periods and check again. And the other way is, and we call those the bottle measurements because we're literally picturing neutrons in a bottle. The other kind is a beam measurement. And there, it's actually very similar to what NAB is doing, where you have a beam of neutrons passing through your experiment and you look for the appearance of protons in some well-defined fiducial volume. That's the difference. It's a very well-defined fiducial volume. So you could say that per this density of neutrons, I see this many protons appearing. And the joke is that this kind of experiment sounds really easy, but it's really actually hard to do. And this sounds hard, and it is hard. So in the end, both kinds are fairly difficult to do. And this is the fun part. This will tell you why the uncertainty for the neutron lifetime is still big. So this is obviously not all time, but the last couple of decades, when I came to the field, this was the neutron lifetime as a function of time. So, and there are results from beam measurements, which are the red squares, and storage or bottle measurements, which are the blue circles. And, they're kind of approaching, converging on some number. And the yellow line is the particle data group average. And this was the early 2000s. And then the year 2005 came, and things got very exciting. This result was published. Not only did it have spectacularly low uncertainties, it was also very far from the particle data group average and the other results. And then since then, 2 more were published, not as competitive, but pretty good and lower down. So now it's like, okay, what's going on? Are all new measurements just slow or what? So the particle data group did not incorporate this number in 2005 because it's just so far off from everything else that was going on. It just says, no, you guys, you being neutron physicists, you figure this out. In the meantime, these previous measurements came under some scrutiny. 1 was retracted and 2 were reanalyzed with new results having new lower values. So now there's basically no high values left that were obtained using storage approaches. Everything that's high appears to be from a beam experiment. And on average, they don't have very competitive uncertainties compared to the bottle ones. And the bottle measurements are all living below. So updating it to the modern times, there's a couple of other measurements since then. It basically looks like this. We quote 1 average for the storage experiments and another average for the beam experiments. We obviously don't include this value. This is a new program at JPark. We're very excited about it, but it's still starting up. So I think it'll be a little while before they have a competitive result. So this is a 4 sigma uncertainty, and in particle and nuclear physics, anything more than 3 sigma is potentially troubling. So this is where we are today. And as you can see, there's really just one beam result. Because the Byrne publication is an earlier instantiation of the same experiment. So guess which one I work on. I work on the U apparatus, and I'll get to it a little bit later, but kind of the pressure is certainly on this result, right? Because they're basically the only one that defines this band. Okay. And just a little bit of a historical note, this experiment was originally done and published in 2005, but there was one source of uncertainty that had to do with neutron counting, the method that was used to do neutron counting, that was addressed in a separate standalone experiment, allowing for a reevaluation of both the result, but mostly the uncertainty. So this is the same experiment, just one systematic uncertainty was reevaluated. So if you see older plots, sometimes it'll appear in the same year as Serebrov's result. Okay, so I showed you this plot earlier, being like, oh my gosh, it's hot, so messy. Well, now this is the particle data group value for the neutron lifetime, which does not include the beam experiments. If we just put the beam experiment band on here, we're just filling in the whole thing, and anything can happen. So from one point of view, a person can say, wow, you guys really don't know what you're doing. Or from another point of view, you could say that our experiments are maybe getting precise enough and sensitive enough that we really have to evaluate the methods and make sure that we really understand everything that we're doing, and all the systematic uncertainties are not only being evaluated properly, but are being evaluated. Maybe there's something that we haven't thought of at all. So as an experimentalist, untangling this is kind of a fun prospect. So in the last few minutes, I just wanted to talk a little bit about how these measurements are done and what the big difficulties in them are. So in the bottle measurement is where we use those ultra cold neutrons, which can be confined with materials, or you can make a magnetic bottle, a very specialized magnetic field. And you wait for a while and you see how many neutrons are left. The thing is, what you're measuring is something we call a holding time. It's not really the lifetime of the free neutron, because neutrons can disappear in other ways, not just from beta decay. So what you're measuring is actually some combination of all these processes, and you have to correct for all these other things. The premier experiment, in my opinion, just because I think it's really cool, of this kind is the UCN Tau experiment, which lives at Los Alamos National Lab, and they use a magnetogravitational trap. So they have this bowl type thing made of 10,000 permanent magnets, and that lives. So the neutrons are kind of fed in from the bottom, and then they levitate inside this trap. And the gravitational part comes in from the fact that it's not really closed on the top. Like they're levitated kind of in 2D, but because these are nano electron volt energy neutrons, it's deep enough that they actually can't get out. They don't have enough energy to hop out. This and that experiment, actually, let me just go back a little bit. That's the PADI result over here. So it's just a really cool way to do the experiment. So, but as I said, the correction to go from what you measured, which is the storage time, to the lifetime can be really big. So when these experiments started in the 80s, like the correction was huge, but they're still claiming fairly small uncertainties. And this is that PADI result, the UCN Tau experiment. I did not forget to draw the line. That's how small their corrections are. That's how well they understand their experiment. The correction to go from the storage time to the lifetime, I think, is on the order of a second or so. It's very small. So we can't say that you don't understand that. So this experiment is really pushing the limit. So finally, I come to the thing I'm working on in the last few minutes here. So the beam experiment. So we're measuring dN/dt. We have a beam of neutrons that passes through some volume that we've defined as our fiducial volume. This is where we're going to look and wait for protons to appear. So it has to be a very well-defined volume, and we have to have some way to grab those protons out of the beam and say, this is it. And at the same time, we're also monitoring the neutrons that pass through this volume. So we need to know the neutron density of that volume and also grab the protons that appear in that volume. So we don't really grab them, we trap them. So we build this segmented electrostatic trap that kind of surrounds the beam of neutrons. So the neutrons come in and they just pass through. But as I mentioned earlier, these protons that come from neutron beta decay, they don't have a lot of energy. They have at most 750 electron volts. So if I make this segmented trap such that I can put 800 volts on the ends, then the proton cannot get out of the trap in the longitudinal direction. Then I take this whole trap and put it inside a superconducting magnet with a 4.5-ish Tesla magnetic field. Well, now I have confined my protons in all three directions, and they just sit there inside the trap, and the neutrons are still streaming through. Once in a while, we open the trap and let our protons out. And we do that via having a creative magnetic field. So the magnetic field in the magnet has a churn. So the magnetic field turns, and as the protons come out, they follow the churn in the magnetic field, and the detector actually sits off to the side. So that's the principle on which this experiment works. So you have to count the protons, and you have to monitor the neutrons. And from the BL1 measurement, the only one that's published, actually, you can see that it was the proton counting statistics, the uncertainties were about 1 second, which is competitive with the bottle ones, and it was systematically limited. This is what I previously referred to as that point moving. The method of counting the neutrons had a large uncertainty associated with it, and it was something that the experiment couldn't get past. A standalone apparatus was created that can be a colloquium in its own right, that was basically able to reduce the uncertainty on these first three terms combined to basically half a second or so. That's why we're now running this experiment again. We made some other improvements, and that's why we're calling it BL2. And ideally, we can probably get down to 1 second. In the reality, we probably won't, just because of time constraints. So we don't actually know what the final uncertainty on this is going to be. But we will evaluate the method and make sure that we, because, you know, when you have a 3-second systematic uncertainty, you maybe didn't look at everything else as carefully as you could have. Really trying to make sure that we understand the method and there's not some fatal flaw before we go to the next level with the new apparatus. So this experiment does not live in Tennessee. This lives at the National Institute of Standards and Technology reactor, which is outside of Washington, D.C. in Gaithersburg, Maryland. Once again, not a nuclear physics facility. But we're taking advantage of this new beamline that was built, Neutron Guide C, NGC, always fun to have photos. And the experiment itself is not huge. You know, this is a helium tank for reference. This is the magnet inside of which that our proton trap lives. This is what a proton looks like. And this is after it has been accelerated with a 30 kilovolt potential, just like in NAB. All these protons need acceleration. And the detector is 100 Kelvin, so it's cold. It's not a huge signal, okay? And the way we actually get the neutron lifetime out is we do this for a bunch of different trap length. That's why it's segmented. We look at the ratio to neutron to proton ratio as a function of the trap length, because like I didn't, if you want to know more details, you can ask later, but basically it's to eliminate any end effects in the field. So the neutron lifetime comes from the slope in this measurement. So the fact that it's segmented allows us to make a long trap or a short trap. So it's a very clever experimental design. Sorry, the experimentalists are not the only ones working on this. The theory sector has also been hard at work trying to find not necessarily experimental explanations, but physics explanations for why two different methods could potentially give you different results. And this paper this is a PRL that was published a couple of years ago that offered a dark matter interpretation of this anomaly, saying that, so this is my graph, but you know, the dark sector. In addition to the neutron decaying into a proton, the normal way, maybe it also can decay into dark matter. And they proposed 3 different channels. And for the ones where there is something that can be measured, like I think the electron-positron pair, like the neutron people, of course, went back and scoured the data and set limits on this channel. But this was not without controversy, because this was published in, I think, April of 2018 in issue 120, and issue 121, of course, had a kind of rebuttal saying that the fact that neutron stars exist and of the size that they do basically exclude large dark baryons. This is far from settled because, of course, these folks went back and made modifications and blah, blah, blah. But basically, this is unlikely to be able to be settled. On the theory side, we do need experimental agreement eventually. And we're unlikely to do it with our current apparatus just because it wasn't built to have the sensitivity that we need. So that's where BL3 comes into the future, comes into play rather. We're also building an experimental apparatus that can do a 0.3 second measurement. And remember, maybe from what feels like a long time ago, while we don't need a 0.3 second measurement for Big Bang nucleosynthesis calculations, we need something like this for the standard model tests. So we wouldn't be able to do the standard model test with our current apparatus anyway. So we're working on it. We're working on designs. We're working on funding. The approach is the same, but there's a number of technological improvements that we're going to take advantage of, and hopefully this is going to materialize in the next few years. I told you about experiments that are taking data and will be online to take data in the next few years. So this time will actually be very exciting for my field. So there's some tension in the neutron beta decay sector, but hopefully the results from these upcoming experiments will help us disentangle what's going on. So stay tuned and we'll see what this plot looks like in a couple of years. Thank you.
Thank you very much for this very nice talk. If you also appreciated the talk, please write so. If you're in the Zoom session, in the Zoom chat, or if you're on YouTube, please write something in the YouTube chat. I'll be able to share your comments with Professor Fomin at the end. I can send her the transcript. So we already have one question that's queued up in Zoom. So just a reminder, if you'd like to ask a question in Zoom, please use the raise hand feature to move your name up to the top. And if you'd like to ask a question on YouTube, please type it into the chat. Your question will be passed on to me. So our first question, if I just allow people to unmute themselves, our first question comes from Professor Jim Klein. Jim, please go ahead.
Hi, thanks for that nice talk. And about this last thing you mentioned, I just wanted to point out that some of us at McGill noticed that if you allow for dark photons to be in the game too, then the dark matter has a dark Coulomb repulsion in neutron stars that prevents them from accumulating too much. So that's one way of getting out of that objection that was pointed out by those authors.
I knew there was follow-up, but honestly, I was not super in the loop. So good to know.
And just one quick question. You kept showing a proportionality between VUD and the decay rate, but I thought it's supposed to be VUD squared because...
it might be. I didn't, I would literally have to look it up.
Okay, because you have to square the amplitude to get the decay rate.
Okay, I would have to like go all the way back probably.
Okay, but it's not important.
Okay.
Anyway, I just hope that your new experiment continues to confirm this discrepancy.
it's the fun part. I hope my new experiment gets funded. But
Thank you.
Yep. I'll just go back to the end.
Okay, if anyone else is interested in asking a question in the Zoom session, please use the raise hand feature. We've still got a few minutes for questions. If it's okay, maybe it's allowed. Maybe I'll ask one myself. I'm actually a bit curious. So this discrepancy between the beam and the bottle experiments that you showed in the early years before 2010, so the bottle experiments seemed relatively consistent with the beam experiments. And you said that later they were retracted. To what extent is this confirmation bias? And to what extent is this really...
So I don't know how much I can say without putting my foot in my mouth. So two of these were, only one was retracted and two were reanalyzed, which is to say some corrections were recalculated with newer models, things like that. The controversial part of it, I think, is at least one of these were done in consultation with the folks who did this experiment. But time has passed and this measurement has stood. And the new ones from groups that are completely unaffiliated with them are also coming out low now. So there's a lot of pressure on us with our next result.
Yeah, I mean, I guess it just highlights how difficult these things are.
Yes.
If there are other questions in the Zoom session, please go ahead and raise your hand. And if you want to ask a question in YouTube, please go ahead and write it in the chat. We could have questions for the next couple of minutes. I don't see any coming up. Oh, there is one question in Zoom from Heliudson Bernardo. Could you please unmute yourself and ask a question?
Yeah, it's me. Can you hear me?
Yep.
Okay, so first of all, thanks for the very nice talk. I would like to know some extra details about how the neutron beam is produced.
So, it's produced, so it kind of depends on if you're at an accelerator facility versus a reactor. So at the spallation neutron source, which is the one I think I have a picture of, which is the one here in Tennessee, we actually have an accelerator that accelerates protons, or rather hydrogen ions, and then it strips the electrons off. And those are accelerated and bunched into, like proton bunches. And they're released and onto a target, which actually lives right here. And this is a liquid mercury target. And at Los Alamos and in the future European spallation source reactor, it's likely to be a tungsten target. It's something that has a lot of neutrons because we don't actually make neutrons. The protons in the spallation process, they boil off neutrons along with all kinds of other particles from the mercury nuclei. And this is encased in meters of shielding. We shield for everything else except neutrons. And then the neutrons basically come out in every direction, which is why we build our beamlines around them. And they're moderated, which is to say just slow down, because otherwise they come out with very high energies and we can't actually do any measurements. They're moderated usually through supercritical hydrogen, just because it's off of the principle of collisions with something similar. So that's like in the case of spallation neutron source, that's how we get our neutrons.
So when they pass the detectors, they are accelerated or they're inertial?
Which detector?
Well, you said there's a proton detector. Sorry, proton detector to detect the decay after the beta decay, right?
Right.
The experiment, yeah.
Right. So the protons. So the protons are detected, with a normal charged particle detector.
Yeah.
And the neutrons, the way we detect neutrons, there's a couple of different ways, but the way we do it in this experiment is we actually have a lithium-6 foil that would capture the neutrons. And then there is a decay process, and we measure the alphas and the tritons from that decay process.
Okay.
So that's how we do that.
Okay.
Yep.
Okay. Thank you so much.
Sure.
Thanks.
I see a question in the chat about.
Yeah, there's a question in chat, but maybe Professor Thomas Brunner wants to ask it in person. Thomas, do you want to ask?
Yeah, sure. So just to get an understanding of how many experiments are actually planned on a global scale, are there other experiments outside of the US? And so in particular, the in-beam decay experiments. So
to my knowledge, the only in-beam, the other in-beam effort is in Japan. And that's this one. And they're doing, it's technically an in-beam measurement, but they're using a different approach. They're using a time projection chamber where they're going to detect both neutrons and protons in situ. So it's a completely new approach. So, it's taken them time to build it up, but as far as I know, there are no currently other plans to do a beam method. So there are other bottle measurements in Europe and in Russia, of course, because this one, even though it has a Russian name, it was actually done at the ILL in France.
Okay, thank you. We have one more question in Zoom from Matteo Puel. Matteo, would you like to unmute yourself and ask your question?
Yeah, sure. I was just curious to understand, how do you collimate your neutron beam, and also how can you count the neutrons before entering the detector?
So we do not count them before they enter the detector. The neutron collimators are a tricky business, because you want to use something that that captures neutrons but doesn't produce gammas, basically. So that's how we collimate them, and overwhelmingly lithium is used for that sort of thing. And it can be embedded in different things, like there's lithium fluoride collimators and skimmers, and there's something else. But yeah, mostly neutron absorbing material that hopefully, and you can use something that produces, I guess, gammas as long as it's far enough away, far enough upstream.
Can I ask another question? This is related to the answer.
Sure.
So if you don't count the number of neutrons at the beginning, at least before entering the detector, how can you know the difference at the end?
Oh, you mean the other experiment?
Yes.
This one, yes. Okay, so this is a thing I actually didn't understand for a very long time either. So, and there's a few things. One of them is that they characterize the UCN source so well that they can basically tell you how many ultra cold neutrons it produces in a certain period of time. The other way they do it is, I don't have a plot of this right now, but they fill it with ultra cold neutrons from the bottom. They have added a pipe up here with a neutron monitor that where neutrons with slightly higher energies might escape and hit the detector, and they use that as a sample of the distribution to monitor the rate.
Okay, I see. Thanks.
Mm-hmm.
Thank you for the question. So let's thank Professor Fomin once again for a very nice talk and really interesting topic. So I'll close out the session. Those of you who do not have tenured or tenure track positions, please stick around for the après colloque. Don't go away. And that concludes this edition of the Physical Society Colloquium. Thanks to all who have joined us. Please join us again next week for a talk by Valerio Lucarini of the University of Reading entitled Dynamical Landscape and Multi-Stability of